recall from the last lecture, so this is 4.1 continued still. There's a lot slammed into 4.1. Definition of exponential function, and graphs of exponential functions, and compound interest, which is the most interesting thing in this section for sure. So we found that compound interest, the amount in an account, A of t, so at some time where time is measured in years, the amount in an account is dependent on a lot of things, but a lot of those things are fixed. We have the principal, so that's the amount you're going to drop into the account. You've got this weird relationship with the rate of interest, so that's R for rate of interest, over the number of times the money is compounded, or rather the interest is compounded per year, all raised to the n again, that number n coming up, times t. So finally, the variable t is up in the exponent position, hence why this is considered an exponential function, because the thing that is varying is up in the t position. Now, for these problems, you may say, well, does it really vary? Because in every problem, you give me all of these numbers, like you give me p, the principal amount, you give me the rate for the account, you give me the number of compoundings, and you give me time. So I just want to say that we still consider this as a function of time. And since the variable is time and time is up in the exponent position, this is still considered an exponential function. Okay. So what I want to do in today's lecture to build into section 4.2 is I want to look at what happens when we increase the number of compoundings. So let's fix, and when I say fix, I mean like hold constant the value P, R, and T, and see what happens as n gets larger. So we will play with the value of n, where remember n is the number of times the interest compounds. And you hopefully are thinking like the more compoundings should mean more money. So I actually want to draw a little quick picture of that just to kind of give you an idea of what I'm talking about. So say you have some interest account that only compounds interest one time a year. So you've got some lump of money. I'll just denote by this ball or this circle. This is your money. And then one time per year, they add a little bit onto it. So this is one time per year. The sum of money gets like a little bump, right? Little interest, and it gets like very slightly bigger, right? That would be like one compounding. So this would be like an n equals 1. They only compound your interest once per year. Now imagine if you had that same sum of money at the beginning, okay, and then they add a little interest to it, and then they're going to compound it 4 times a year this time. So this span of time is still a year, but they're going to do it 4 times within the year. So first your money gets a little bit bigger, right? And now when they calculate the interest on this, the little bump is going to be bigger because it's based off of a bigger sum of money, right? The little interest bump is going to be slightly bigger because interest is based off of that lump sum that's in the account, right? So the interest gets slightly bigger. So now your money gains a little bit more than it did before, right? And then now the interest gets even bigger because it's based off of a bigger sum of money. And finally, and I'm going off the paper here, but excuse me, you end up with finally even more money. So this would be over the same amount of time, right? Compounding once per year means they only add interest in once per year. This would be a quarterly compounding, where each time they're adding interest, and then the interest is calculated on that new higher amount. So we should all be on the same page when I say intuitively, more compoundings is better, right? Let's actually investigate this mathematically, though, without these ugly pictures I'm drawing. So let's see what happens specifically when n gets larger. And if we're investigating when n gets larger, we want to keep everything else constant, right? We don't want to play with the rate or anything like that. We're just trying to investigate n. So just for simplicity's sake, let's let p equal $1,000. And let's let r equal something sort of realistic like 8% maybe. And let's let time, just for the sake of simplicity, oh, I don't know. I was gonna say 1, but that's not super interesting. So let's just keep time fixed at 5 years. Okay. So what we're gonna do now is we're gonna set different n values and see what happens to the interest. So there we go. Let's say a of t is equal to 1,000 times 1 plus, and recall that whenever you got r as a percent, got to convert it to a decimal. So I should really say right here, this is the same as 0.08, converting that to a decimal. Just take the percent, divide it by 100, right? That's how you get it as a decimal. Sorry, I'm trying to keep that formula on the page. Okay, so I'm going to say 0.08 over, and I'm going to let n be 1, right? Let's just start at n equals 1. So there's my 1. And then up in the top, I'll have n, which is 1, times t is 5. Okay. My next one will be a of t equals, I'm going to go ahead and write them out. And actually, it'd be a great exercise if you guys calculated these to make sure you know how to calculate these in your calculator. I'm not asking you to do this by hand, obviously, right? See if, in fact, let's see, there are 3 of you here today. I'll write down the first 3, and then I'll ask each one of you to compute each of these. Or I'll assign 1 to each of you is what I'm trying to say. So let me get these down. So the second one will be n equals 2. So this is for n equals 1, this is an annual compounding. That's just 1 time per year. This would be semi-annual. That's twice per year. The next natural extension of n is quarterly, which would be n equals 4. So I'll say 1,000 times 1 plus 0.08. So n will be 4 in this case. This is for quarterly compounding. Okay, so I'm gonna assign you guys to do these 3 while I write down the last 2, and I'll calculate the last 2. So let's see. Makira, can you do this one? So I'll just put your name, your initials here so you know which one. Makira, if you could do this one and see what you get. And Maya, if you could do the second one, the semi-annual one. And then Kimberly, if you could do the quarterly one. So what I'm asking you all to do is plug these into the calculator and see what you get. And I will finish writing these. I'm gonna have to scoot the paper up a bit. I'm going to write the last 2. And okay. And quarterly, what's after quarterly is monthly. That's when n is equal to 12. And daily is the last one, which is 300 and 365. Oh, 65. Okay, so Makira, do you have the answer for this first one? Maya, do you have the answer for the second one? Okay.
I'm working on it.
Okay. And Kimberly, do you have the quarterly one?
I got 1,485 and 95 cents.
You said 1,485.95?
Yes.
Okay, cool. That seems about right. So I'm just gonna recalculate all of them just to make sure. So I would say in my calculator, I would say 1,000 times 1 plus 0.08 divided by, which one was that? 4, and then raised to the 4 times 5, making sure I wrap that in parentheses, or I could just say raised to the 20 if I know that 4 times 5 is 20. Yeah, good. Yeah, and rounded to the 100th place because it's dollar amount. Good, good, good. Okay, Makira, how did the first one go? Okay, I will calculate the first one then. And since I've already got it plugged into my calculator, all I have to do is go scroll through and change those numbers. So I'm getting 1469.33. And Maya, how did it go for the second one, the semi-annual compounding? I'll just go ahead and tell you what I got. I got 1,480.24. Okay, so we'll consider the differences between these after I get the last case. So I'm getting 12 raised to the 60. Oh, no, not 605. 60. So this is giving me 1489.85. And then finally the last one, 365, and then raised to the 365 times 5. And I'm getting 1491.76. Okay. Now that we have all of these values, what I want to do is consider how much the money is growing when we hold everything constant, but we're just looking at how the number of compoundings goes up. And also consider like that the jump from monthly to daily is huge. Oh, let me turn my light back on. Okay. Monthly to daily, right? From n equals 1 to 2, I doubled. And then from 2 to 4, I doubled again. 4 to 12, I tripled. And then from 12 to 365, that's a huge jump, right? More than 10 times. So let's see how that reflected over here in these results. So I clearly see that it is going up, right? What's the difference here? The difference between, and I'm just going to say like approximate difference, from here to here was, I'm just going to say like $11, right? Roughly $11. So I'll say approximately $11 difference. Okay, so that's a difference, right? $11. I mean, I wouldn't complain getting another $11, right? What about from here to here? Now the difference is only more like $6, $5 or $6. Oops, dollar sign. Right, and then from here to here, the difference is only $4. And now here comes the huge jump from monthly to daily. This is where they're compounding your interest every single day of the year. And what happens from monthly to daily? That difference is only about $2. So yes, the money is increasing, but it's increasing at a decreasing rate. In other words, what I mean is if we took this n and made it like 100,000, the difference from 365 to 100,000 would be pretty much like negligible. Like once you get to high enough numbers, it stops increasing. It reaches a limit. So compounding, even though it seems super powerful and that you would, the more compounding, the better, that's not necessarily true. It's true for small numbers. More compoundings is pretty much better overall for small numbers. But once you get past a certain point, you reach a limit to how much money the account is earning. You don't end up getting infinite money, right? So that's a pretty interesting thing. And the reason I'm pointing it out is because it takes us very nicely into the natural exponential function. But first, well, there's APY as well. That would throw us off. Okay. So now I'm going to pose the question of what if we let n try to approach infinity, the number of compoundings approach infinity? Like, what if we let the savings account compound interest not just every day, not just every hour, but every second of every millisecond, every microsecond, continuously compounding? So that is, what happens what if we let it compound interest continuously? We do not reach infinite money, right? That's kind of what I just sort of show. I didn't really show it, but I at least showed you how it's going at a decreasing rate. There is a limit, and that limit is coming from this relationship, which says that if we let 1 plus 1 over n raised to the n, so ignoring time, ignoring the p value, making time and p and r all just be the numbers 1, so we can just play with n here, then this approaches the number E, which is a button on your calculator you've probably seen before. It's a very special number called E, which is approximately 2.718, blah, 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 blah. It's a irrational number, so it goes on forever. So we'll either use the calculator to do calculations or we'll approximate it. This approaches the number E as n gets huge. As n tends to infinity, that base of the exponential function, so what this means is the base of the compound interest formula turns into the number E. And there's some algebra that I'm kind of brushing under the table here because I don't want to get into it in detail, but what I'm building to here is a new formula for continuously compounded interest. And here it comes. For continuously compounded interest, Well, I called it a formula. It's more like a function. I mean, you can call it a formula. That's fine. I'm going to say function here, though. We use the function a of t equals. So the p is still going to be there, the p principal amount. And then all of that, like parentheses 1 plus r over n, all that stuff, it just gets like sucked up into the letter e. And then because of the algebra that I said I'm brushing under the table here, what ends up happening is the letter r stays in the exponent position along with the variable t. So it's p times e raised to the rt, where e is that number 2.7181 blah 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 blah. Super important number for exponential functions too. So what I'm doing here is just to kind of remotivate what's happening here. We're looking at exponential functions. We considered very nice examples of real world examples where exponential functions can be used, which is compound interest, right? So we had that nice formula for that. A of t equals 1 plus r over n raised to the nt. Oh, I think I forgot the letter p. The p is in there too, right? I think I left it out. Anyways, so we looked at those examples. Those examples built up to a new kind of compound interest formula or function. And we're going to play with this a little bit. We'll solve some problems with it. And this also will open the door to the so-called natural exponential function, which is going to be a special class of exponential functions that have this base e. So this is one of them, but this is a special real-world example. But the general functions with base e, exponential functions like e to the x, they're just super, I mean, it might be the most popular function in math because you can do all sorts of stuff with it. Really, you can differentiate it, integrate it. You can do all sorts of crazy stuff to it, and it acts very nicely. So there's a reason it's so popular. But first, let's do an example just using this formula, so I can, so you know how to use it. So let's calculate. I guess this is first example for today. Example 1, calculate the interest on a continuously compounded savings account with an interest rate of, let's say 12%, with a principal of, let's say $15,000. Oh, and time. I have to give you a lot here, right? I have to give you the principal, the interest rate, how much it compounds, which I've said continuously compounding, right? Calculate the interest on a continuously compounded savings account with an interest rate of 12% with a principal of $15,000 over, let's say 6 years. So if I'm asking about compound interest, you should be thinking, okay, I'm going to use one of those two formulas, one of the two A of t formulas. Either A of t is p times 1 plus r over n raised to the nt, and I have to say what n is. Is n, if n is semi-annual, or if it compounds semi-annually, then n would be 2, for instance. In this case, it's continuously compounded, which means I go to the other special formula for continuously compounded things, which is going to involve that letter E. So I'm going to say A of t is equal to the principal, so 15,000, times E raised to the 0.18, right? 0.18. Let me rewrite it. Raised to the 0.18. That's R. That's the interest rate. Oh, why am I saying 8? I have no idea. What is happening? I'm sorry, I'm distracted. My girlfriend's cat is like trying to get in this chair with me and it's distracting me. Okay. Let me try this one more time. 15,000 E raised to the 0.12, which is the interest rate R written as a decimal, and then times T, which is 6. To calculate this, I'll show you how to do it in the calculator. You will do 15,000 times, and you got to find the E button, which for me it's above the natural log, the ln button. So it's second and then E. So now that opens up the E function for me, and then I'll say 0.12 times 6, close the parentheses up there, and I'm getting the amount in this account is $30,816.50 when I round. Oh, in dollars. So just a word of advice, if you are like later on in life looking to open a savings account and you're comparing banks, the interest rate matters more than the number of compoundings. Like if you see this account that has a continuously compounded interest, number of compoundings is continuous, and they have an interest rate of 12%, and then there's another bank that compounds quarterly, but they have an interest rate of 15%, then you would want to do the calculation to be absolutely sure, which you know how to do now, to compare them. But I would probably think that the one with a higher interest rate is almost always going to be better, because compoundings, the number of compoundings, as we've seen here, is not as powerful as you might think, because it approaches some limit. In fact, with the amount of money we were looking at earlier, with the $1,000 at the 8% interest, the difference between an annual compounding and a daily, oh, you know what? Let's calculate what it would be for continuous here. Now that we know how to do that, let's calculate that right here. So I'll say for continuously, A of t is equal to 1,000 times E raised to the 0.08 times 5 is what we let t be there. So this is for continuously, the special case. Like, what do we think the difference is gonna, is it gonna be a huge difference from annual to continuous? Well, let's see, 1,000 times E raised to the 0.08 times 5, 1491.82. Look at that, it's barely bigger. What did I say? Yeah, 1491.82. I mean, look at the difference from daily compounding to continuous. It's literally cents. Over 5 years, that's the difference, right? And the difference overall from an account that compounds annually to an account that compounds continuously with the same interest rate is only like, what, $21 or so? So yeah, about $22 from here to here. 22 extra dollars. If you upped this, if you took this case, annual only compounds one time per year, and you upped that interest rate to 9%, I bet you this would be bigger than that. Just 1 extra percent, I bet it would be bigger. So in fact, can I say, We could just calculate it, but anyways, word of advice, be wary of someone trying to convince you to open a savings account at a bank based off of the number of times it compounds. If they're pushing that, then they think that you don't know the strength of compounding versus the strength of an interest rate. The interest rate is stronger. Okay. What's next? We have some, what is next? Some things to talk about E. Though I skipped the APY stuff, but I don't really care for you to know that APY. APY is a thing called annual percentage yield, or rather that's what it stands for. If you know, I'm guessing probably most of y'all are not in the place where you're thinking real hard about, you know, where to open a savings account. You're probably like, if you have one, you're using like your parents' bank maybe, or you're just not worried. You don't have enough money to be worried about it probably at this point. Later on though, you know, when you are dealing, you know, with opening a savings account and really comparing different banks and stuff like that, you'll want to know about this thing called annual percentage yield. And without getting into it too much, it's basically like how much money you would make on this account if it was a simple, no, I said that wrong. How much the interest rate would be on this compounded interest account if the interest, if it was just a simple interest bearing account. So again, I don't want to get into it too much. I don't think we need to know it right now. But if it comes up, you could always go crack open your math textbook because they define it for us right here on page 371. Though you could probably find something easier to read online just by Googling it. Okay, so let's talk more about this exponential function, the natural exponential function. So more about the number E. So the natural exponential function is it is an exponential function, of course, is the exponential function. It's a little bit redundant to say that again, but that's okay. Is the exponential function. And what do exponential functions look like? They should, algebraically, they look like a to the x, where a is some positive number, right? Not equal to 1. And for us, that number is going to be e, or rather for the natural exponential function, the base is going to be e. So we say with base e. Sometimes this is just called the exponential function. Like if someone's talking to you about math and they say, oh, it's an exponential function, then that just means like any kind of exponential function. But if they say the exponential function, that's this one right here. This is, like I said, probably one of the most important, probably the most important function in math, especially in like modeling things. Let's just practice using it. Example 2. Just get some practice. We've already done some practice with the continuously compounded interest, but let's calculate each. And let's practice rounding too. Part A, let's calculate e cubed. And part B, I'll go ahead and write down all the parts here. E2 times e to the negative 0.53. And part C is e to the 4.8. So pop these into the calculator and round to 5 decimal places. E cubed, so in my calculator, I'll say, I'll hit second and then the natural log button to get to my E button, then I'll put 3 and I'll close parentheses. I'm getting 20.08553. Does it say, is it 5 decimal places or 5 significant figures? 5 decimal places, so 20.08553. That's that round. Oh, no, I rounded wrong. 4. Ha, 4, because the number after a 3 is a 6, right? So I round the 3 up to a 4. All right, part B says 2 times e raised to the negative. So that's fine. You can raise e to negative numbers because e is an exponential function. It has unbounded domain. You can plug whatever you want into it. 2 times e raised to the negative 0.53. Make sure when you're using your calculator that you use the negative and not the minus sign, because if I use the minus sign, it's going to say syntax error. And when I say minus, I mean like the subtraction symbol. So instead, make sure you're using the negation symbol so that the calculator knows what you're talking about. Now, when I round this, I'm going to have 1.17721. Okay, and then part C, e to the 4.8. So again, just e raised to the 4.8, close parentheses, 121.51042 when I round that. Make sure you know how to use your calculator, how to plug this stuff in, how to evaluate it, how to round appropriately. So one thing we should note here is the domain is completely unbounded because it's an exponential function, right? It's not special in the sense that it has like a weird domain or a weird range. So let's note that f of x equal to e to the x has the same domain and range as a, quote, normal, or, you know, something that has like 2 to the x or 3 to the x exponential function. The ones that we investigated last time, or yeah, it was last time, or this whole week pretty much, right? And by the way, just so you remember, the domain is all the real numbers. So I could denote it like that, or maybe you've seen it like this with a capital like bold R, like the R with the 2 legs. These mean the same thing, all real numbers. And then the range, regular capital R for range, is 0 to infinity, right? It can never touch, it has that horizontal asymptote at the y-axis. It can never touch, sorry, the x-axis. Has a horizontal asymptote at the x-axis. It can never touch the x-axis. Never touch a y value of 0. Because recall, the range represents the y value, so it can never touch that 0. It can get super close. So again, this is not why E is special, because it has the same, it's the same as the other ones. E is particularly special because of that limiting definition that I wrote down for you earlier, which I know may not make a whole lot of sense to you right now, and it won't until if you ever have to take calculus. But this thing approaching E as n tends to infinity is a super powerful expression or formula or relationship. It's and it pops up just all the time in math. So that's why this thing gets its own name and everything. Okay, let's look at the graphs of it, even though the graphs aren't really going to look that much different from other exponential functions. So let me go to share. What? Am I sharing? There it goes. Okay. And go to Desmos. And we'll hit e raised to the x. There it is. It's like really nothing special about it, right? It looks like an exponent. Like for instance, if I graph 2 to the x and 3 to the x, functions that we've already seen, it's just kind of like one of those, right? It acts pretty much the same. Whoa, what just happened? Sorry, I'm still not used to this laptop touchpad sucks. Let me get my actual mouse. Oh, God. Kitty, that is not a good place for you right there. Okay. So it pretty much acts like the other exponential functions, right? It asymptotically tries to touch this x-axis, but it never will, right? We know no matter how much we zoom in on this function, it will never actually touch this x-axis. It's got that horizontal asymptote. It does not have a vertical asymptote as we go up, right? It blows up to infinity really fast, just like other exponential functions, but it never approaches like a vertical line. It's going to keep growing to the right as well as up. Oops. We also see that it's going through that same point that all the other exponential functions go through, 0, 1, because e, when you raise e to that input of 0, e raised to the 0 is 1. Just like any other number, any number raised to the 0 is still 1, hence why this coordinate point is on the graph of this function. What else can, so yeah, you know, the graph's not really that much different, right? It's not that it grows way faster, because I can pick a faster growing function right here. The 3 to the x function grows faster. It gets taller faster. Again, it's just special because of that relationship dealing with the 1 plus 1 over n raised to the n as n tends to infinity. Okay. All right. Okay. So, since it's so special because of that behavior, that limiting behavior, what are some examples where it can be used in real life besides continuously compounded interest? Example 3. Here we go. An infectious disease begins to spread in a small city, of population 10,000. After T days, the number of people, so you know when you're watching the news about the coronavirus back, you know, maybe not so much now, but a year ago, there was always these new numbers coming out, like scientists had taken what we know now and extrapolated that to say, oh, this is how many people are going to be sick in a month or whatever. All these things are coming from models, exponential models. That's where those numbers are coming from. After T days, the number of people infected is modeled by the function. So that word modeling coming up again, modeled by this exponential function here, which we'll say v of t. They called it v for like virus, maybe. 10,000 over 5 plus. So often we will see, sorry, let me finish writing this down before I keep talking. Okay. Often, whenever you're modeling things in real life with an exponential function, they will look very scary. Like, it's not the just, e to the x function that we're used to, that we just saw, right? This is a lot more going on, right? There's a fraction, there's a negative exponent, there's like a sum in the denominator. We see the 10,000 coming up. That's the initial amount here. So building this kind of function, in real life, how do you build something like this? Well, first of all, you got to have a math degree, right? You got to know what the heck you're doing. You got to have all the data. Well, maybe you don't have to have a math degree, but you at least have to know the math, right? You've got to be good at it. You've got to know all of the things that come into play, like all the different parameters that are going to affect like how infectious the disease is, all sorts of things, right? How dense the population might be in certain areas. All these things coming into play. What you do is you run the data through a computer, and then the computer pops this model out for you. You don't build models by hand anymore, right? People build models with computers. They give the data to the computer with the right parameters, and then the computer pops out a model, and then they can use the model to say things about whatever they want to investigate. In this case, they'd want to investigate the future, right? Like how long, or what is the question going to be? How many people are infected on day 30 or something like that? In fact, let's ask that question, but I won't say 30. I'll say how many people notice T is measured in days here, not years like the other real life examples we were looking at for modeling growth in a savings account. T was measured in years. Here it's measured in days. So day 5 is what we want to investigate. So what we do is the model's already built for us. All we have to do is know how to plug this into the calculator, which, might be a little tricky at first, but relative to how hard it would be to build the model, I think that you'll appreciate how fast this will be. Okay, so how would I plug this into my calculator all at once? All at once. Let me show you how to do it. The trick is use parentheses a lot. I'm going to do this all at once. I don't need to do this piece and then this piece. I'm going to do it all at once. 10,000. Okay, there's 10,000 divided by, okay, starting the fraction. Now I'm going to say parentheses, and I'm going to, well, no, I can't do that with this calculator. So never mind. I'm just going to open the parentheses, and then I'm going to say 5 plus 1,245, and then my e function. And then so now my second parentheses is open for the exponent position. And up there, I'm going to say negative 0.97 times 5. That's happening up, that's this part. And now I'm going to close that parentheses. That was closing the parentheses in my exponent. And now I'm done with my denominator. So I'm going to close the denominator parentheses, and then I hit equals. And that's it. And what do I round to? Since I'm dealing with people, I'll round to the whole number, right? So I'll say, I can say approximately 678 people infected. So if the scientist knows what they're doing, and they're working with a statistician or something, or a mathematician, well, probably a statistician, to be honest. And they build this model, and this model, everyone's on the same page, like, yeah, this is a good model. This is what will end up on the news, right? You won't see this, but this data will end up on the news in this city. They'll say, all right, day 1, we've got 21 people infected. By day 5, we're going to have nearly 700 people infected. If we increase at this rate, so everyone needs to, it's a deadly virus, so we need to stay home and wear masks, whatever, whatever the advice might be at that point, depending on how infectious it is. Now, that pretty much finishes 4.2. So with these last couple minutes, I'm just going to talk about what we will be doing in the next two sections, which is about logarithms. And I will motivate that by asking a question of, what if someone said to you a very natural question about this model, this problem? They said, how long will it take for 5,000 people to be infected, for half of the population? How long will it take for 5,000 people to be infected? This model does not tell you that. This model does the opposite. You give it the time and it tells you how many people would be infected, right? So you could play with some numbers to answer that question, right? You could keep plugging stuff in and try to get your output close to 5,000. But there's a better way, which is to take the inverse of this function so that you swap its output with its input so that you can directly ask it the question of, given some number of people being sick, how much time does it take? You invert the function, right? Like we've talked about inverse functions, swapping input and output, right? So in order to talk about inverses of exponential functions, we have to talk about a new type of function called logarithmic functions, which are the inverses of exponential functions. So that'll be what we do in the next section. We'll introduce log functions, and then 4.4 we'll talk about log laws, and then well, yeah, let's just leave it at that for now. Okay, so if there are no questions, you guys are free to go, and I'll see you on Monday.